But there's this, I guess maybe, let me just be a little bit more general about it because I don't know exactly. I have my statistical mechanics books on the other side, but I'm not going to bother with it. Time and temperature have a very, very, very close relationship. That is the relationship between time and entropy. And some people will say that time and temperature is a mathematical relationship and it's not physical. I find that hard to believe. I do. So the point is basically, time and entropy are related, but they're related through temperature. Temperature is the key to understanding this relationship. Well, let's not worry about it. I want to answer Luis's question. Luisa. Luis? Sorry if I'm butchering your name. Many people don't believe there's problems with time, okay? But the fact that we can't even figure out what the relationship is between time and temperature, between time and entropy, is a big issue. And furthermore, the relationship between time, temperature, and entropy has this perception of time being directional, i.e., you only have positive time that you can experience. And the other thing is like you can write the mathematics for negative time and have the reverse light cone and all this other stuff, but that doesn't mean that it's coherently understood between time in all of that sense, in entropy, in cosmology, because we have a Big Bang. So if you want to talk about the start of time, if that's, or like the beginning of time, or if that question even makes any sense, you could talk about the Big Bang as the beginning of time. And that's directional. We believe that's directional, if that's the way that you define it. But yet, in quantum field theory, you cannot treat time that way and be successful. Why? Because you basically make the CPT invariance, that really necessary thing to make your Lagrangian work, doesn't exist if you treat time in quantum field theory like cosmic time. And let me do a little thought experiment to show you how I understand that. And this might be a little bit controversial because this is something I came up with. But it's in my essay. It's on the FQXI website, the Foundational Questions Institute. If you'd like to see more without pictures, you can go there. But basically, here's the idea. Picture a particle decay. All right, we have like something easy, like a photon decaying into a positron and an electron. Okay, that's a simple Feynman diagram, right? Now, time is going to go this way because it's a decay. Okay, so we have time going this way because it's a decay, and that's all fine and dandy, right? In the confines of both views of time, this is okay. Now, and what is the T in CPT? The T in CPT is called Time Reversal Symmetry. And what does that mean? That means what happens if you play time backwards. How do you understand how this works? So I'm going to get Schwartz out because Schwartz is where I got the idea from. Schwartz, the textbook. And it's less likely that I will screw this up. So now I'm going to do 3 frames by 3 frames, okay? So on this side, I'm going to have what I call cosmic time reversal symmetry. And what cosmic time reversal symmetry is, it's directional time. Time is treated like it is in cosmology. We use what's called the free FLRW metric. How bad did I botch that up? FLRW metric? I'm not gonna look it up. It's the FLRW metric, something like that. Someone look it up real quick. So I called it cosmic time reversal symmetry. Basically means that time is unidirectional. If you reverse time, you reverse time everywhere. It's a global thing. So time started at the Big Bang. That's basically this idea, this approach is time started at the Big Bang. If you reverse time, you have to reverse everything. So, that I called cosmic time reversal symmetry. Okay? Over here, we have the time reversal symmetry associated with particle physics. I called that one the Lagrangian, fancy L, time reversal symmetry. Okay? These two are different in the following way, and this is basically outlined in Schwartz. And what Schwartz does, well, let's do it first and I'll tell you what Schwartz does. So in the cosmic time reversal symmetry, you have the original frame. Okay? Time is going this way. Okay, you start with the photon, it then, reverses, it then decays into an electron, positron and an electron. Okay? Same thing happens here. This is the first frame, so there's no reversing of time yet. And this is positive and this is minus. Okay? All right. Let's reverse time again. Or now let's reverse time. So let's go to frame 2. How do I do this? Okay, let's do this. So this is frame 1. This is frame 2. I didn't leave myself enough room for frame 3, so we'll get there when we get there. Let's reverse time. So now we go from t, we'll say from t to t prime, from t to t prime. Okay? Now, in cosmic time reversal symmetry, we just flip time. So you have positron and electron, and the difference is now everything swaps. So the positron, let's read it from Schwartz exactly so I don't ruin it. FLRW metric, awesome. That's what I was trying to say. So I want to read it from Schwartz so that I can be very clear about this. In this cosmic time reversal symmetry, this operator that will reverse time, it takes particles to antiparticles, and it's understandable as the antiparticles as particles moving backwards in time. So basically, as they move backwards in time, so now time is going from t prime to t. Okay, these particles switch roles. They become antiparticles and they annihilate, and a photon is made. Okay? Antiparticle, particle, they annihilate and they go forward. Yes. Okay. Now, what does that mean for the Lagrangian time reversal symmetry? The Lagrangian time reversal symmetry is different. Here, we have to do this. We have to talk about it as if they are random positron, random electron, and they are annihilating into a photon. Okay? So it's not too different yet. Okay? Time again, this way. From t to t prime. Just to a different time. You don't actually go backwards, you're just reversing the process. So the reason I say time to t prime is because this t prime is still later than t. You are just reversing the process. Let's read it what he says. Thus, this is page 201 in Schwartz, the new t makes it look like things are going forward in time, but their momentum and their spins are flipped. This is the time of quantum field theory. So it's just taking, so again, this, particles become antiparticles. You are actually going reverse time, from a later time to an earlier time. This one, you just reverse, or you flip the spins and the momentums, and then you still play time forward. Okay? So now things start to look a little different just graphically, but it's not that big of a deal yet still. Okay? Here's the point. Number 3. Down at the very bottom, which is probably not the best. let's play time forward again. Okay? What does CTRS mean? Well, CTRS is just going to go back from t. Oops, maybe I should give myself more room here. From t to t prime. There's nothing else that can happen here. Okay? Why? Because this already happened. It's right here. Here it is. Here it is. You reverse time, but if you play it back forward again, you're just going to get the same thing because the only thing that changes are the absolute time changes. I said absolute. I probably shouldn't say absolute time. Nevertheless, yes. Now let's play this forward again. Okay? You see that? Yeah. Okay. What does this mean? They're the same thing, right? They're the same thing. So what's the big deal? Because when we go like this, we are now looking at a photon. The photon decaying is a probability. So now there's a probability that this may happen. There's also a probability that it might not. Or if this is a much more complicated process, like say, what is it? Is it a kaon into pions? Or like you can sometimes get 2 pions and sometimes get 3 pions? I think that's it. I wish I had a particle physicist in here to tell me that. That part's a little part that's rusty to me. But either way, the point is this is now a wave function, and it has to recollapse. This is determined. Why is it determined? Because it already happened. It happened, the time went backwards. There was no other future that this could write because the future was already written. That's something by George Ellis, who's another... he said something about the future is, or the past is determined. So if you go into the past, that's determined, then the future up to where you left will ultimately be determined as well. So there's no collapsing of the wave function here. There is collapsing of the wave function here. Well, what does that mean? These are 2 separate things. Here, you have a time reversal symmetry that is determined. Here, you have a time reversal symmetry, and the third frame is determined. Here, you have a third frame that's not determined. Well, what's the big deal? Okay. Well, this is what we think. This is what we see. Reverse the DVD you're watching. What are you going to see? You're going to see everything go backwards. You're going to see everything come forward again, just in the same way that it went backwards. Or the same way that it went forwards the first time, I should say. Right? That's because this is intuitional. This is physical. This is what we see. What's the problem? Well, Schwartz goes on to say that if you follow this standard, CPT invariance is trivial. That's a big problem. Because I spent about 15 minutes at the beginning of the stream trying to explain to you that my advisor's advisor, Greenberg, did something great in the 2000s, and that was to prove that CPT invariance cannot be trivial. It has to be there. It has to be in every Lagrangian if you want your Lagrangian to be Lorentz invariant. So that's an issue. That's a big issue. And this is just my understanding of this issue. There's a lot of people who have done a lot of work of the same issue, just they present it in different ways. This is the way I understood it from a particle framework. This one, where you just always run time forward, it works beautifully in quantum field theory. You get CPT invariance, you get everything that you need, it looks great, it works great, but we don't see the world this way. And that's the issue. So that's where time physics should be going, is to try to understand on a smaller scale why these things happen. Like why we experience something that gives us bad results in quantum field theory. But like I said, some people don't think it's an issue. Some people say our intuition is wrong, that this cosmic time reversal symmetry is just, a flavor of a wrong metric, or that the metric only works on certain standards, and that we can't actually use it for, I don't know, particle physics. I don't know what they would say. They would say a lot of things. And a lot of really, and I mean, I'm not talking about like nobodies. I'm talking about really, really good, solid physicists saying that there are 0 problems in time. But then you get other physicists who say otherwise, like Sean Carroll and Brian Greene, who think time's a big thing. Nima Arkani-Hammad, who thinks that time in particle physics is all screwed up. Hooft, who thinks that time in quantum mechanics is all screwed up. Who else is there?